So now that we've seen several examples of discrete probability distributions, we're going to look the other way and think about continuous distributions. Now, a lot of the same expectations apply here, but they do work a little differently. For example, because a continuous distribution can take on infinitely many values, we can't really talk about adding up individual values like p of x equals 0 plus p of x equals 1. Instead, we're going to always be talking about ranges of values. For example, p of 0 less than or equal to x less than or equal to 1. So we're going to talk about several different continuous distributions before the course is over. But we're going to focus most of our attention on the so-called normal distribution or bell curve. Not only does it have a lot of statistical applications, but it can also be used to describe an enormous range of physical properties, from people's heights to test scores to variations in the weight of consumer products. And the way we're going to define probabilities with a continuous distribution is in terms of the area under the curve. For example, looking at this graph, the probability of a randomly selected item being between 0 and 1 is going to be the area in this section of the graph. Now, to find the area under a curve, we first have to have a formula for it. And the formula for a normal or bell curve looks pretty intimidating at first. But I put this here just to make it clear that the numbers we're going to be using as we go along didn't just get pulled out of a hat. Okay, there really is a formula behind the shape of this curve, but as a practical matter, we're not going to actually use this equation to answer specific questions. So the first thing we're going to do is to narrow our focus down to one specific normal distribution, the so-called standard normal distribution. Okay, a standard normal distribution is one whose mean is 0 and whose standard deviation is 1. So if you substitute those numbers into the formula on the previous slide and do a little calculus, you would see that the total area under the curve created by that formula that I've got graphed here is going to be equal to 1, just like we expect from a probability distribution. Right, and finally, this graph has a very useful property that it's symmetric across its mean. In other words, the left side of the curve over here is a mirror image of the right side of the curve. And more specifically, the area under each side is going to be the same. So this area here is equal to this area here. So I want you to think about what that implies for a minute, because the total area is 1, and each of these parts is the same. The area under each side of the curve is going to have to be 1/2. Okay, now that we have an idea of what the standard normal curve looks like and some of its properties, in the next lecture we're going to see how we can use the curve to determine some actual probabilities.